Okay, this is video homework 3. There's 2 parts, but the second part is on the second page. So for number 1, I drew the graph with the coordinates, and we're given the vector field xi plus yj, and we're asked to compute the line integral over c1. So to do that, we have to parameterize it, which is RT. And for that, we have 1 minus Ti plus 2Tj. These are just the difference in the starting and ending coordinate is all the parameterization is. And then this is from the range where t exists between 0 and 1. And then to actually do the integral, we have the integral of C1 is the dot product of the vector field F and the derivative of the parameterization. So to get the vector field component, we have to plug RT into F, and we get 1 minus Ti plus 2Tj, and then the derivative I wrote of RT right under that is just negative I plus 2J. You dot product those, and then you take the integral, which I showed on the right, then you plug in the bounds, and then you get the answer 3/2. So the line integral of C1 is 3/2. And then for C2, we're asked to do 2 methods. We're asked to use a parabolic curve of degree 2 that joins the 2 points, and then solve the integral by direct integration. And then method 2 is interpret it as part of an ellipse, and then you have to parameterize that with sine and cosine for that one. So method 1 starts in the middle of the page. You parameterize it by just doing the equation of the line, and then you substitute x for t, and then you get the equation of a line in terms of t. Then we get RT, which is just the x and y components of the equation of the line. Take the derivative is right under that, and then plugging RT into the vector field F is right under that, with t existing between 0 and 1. And then all you do is you just plug that into the integral. So from 0 to 1, I took out the negative. Dot product is right there, and then I just integrated it in my head, and then plugging the bounds in from 0 to 1, and you get 3/2. And then for method 2, you find x and y by parameterizing it with like the unit circle. So x is just cosine t, and y is 2 cosine t because the vertex is at 2, and t exists between 0 and pi over 2 because it's just the first quarter of the unit circle. And then RT is just the x and y components of, well, I just wrote them, you can see right there. And then there's the derivative, and plugging RT into the vector field F. And yeah, then that goes into the integral from 0 to pi over 2. The derivative of RT plugged into the vector field F, and that I just used a calculator for and got the same answer, 3/2. I totally forgot to show that this first one is conservative using the curl test, but I did it for the second one, so you can see that there. So if we move on to problem 2, we got the same vector field, but there's like this triangle that I labeled C1, C2, C3. And then I parameterized all of those right there. I guess I should have done them individually, but It's fine. The derivatives and the plugging RT into the vector field F is on the right side for each one. And then I did the dot product and the integral on the left side for each one and got the answers that I boxed: 3/2, -2, and 1/2 for each of the sides of the triangle. And then it says to show that add the results of the 3 line integrals together for the whole triangle and make sure that it is 0. And I did right there. 3/2 minus 2 plus 1/2 is 0. And then it said verify using the fundamental theorem of calculus. The first step of that is determining if the vector field F is a conservative vector field. And to do that, we use the curl test, which is the derivative of the second component with respect to x minus the derivative of the first component with respect to x. They have to be the same so that they equal 0. And I did that at the very bottom. So the derivative with respect to x of the second part is 0, and the derivative of x with respect to y is also 0. So 0 minus 0 is 0, which means it's conservative. And then to find the potential function, you take the integral of the vector field, which is shown in the bottom left. Sorry, the screen recording cut short, but the potential function is written in the very bottom left. And then after you get the potential function, what you do is you plug in the coordinates to the potential function, where f of q is the final set of coordinates. So you plug that into the potential function. And then you do minus f of p, and f of p is the plugging the initial coordinates into the potential function. So I did that for each of those in the little space that I had at the bottom, and got the same answers for all of them that I got when I computed the answer using the line integral. And then that was it. So